Imagine that you are a designer and that you got tasked with designing a new web application. You create a couple of screens and you soon discover that you're reusing certain elements over and over again. You then isolate those elements to be able to copy-paste them more easily. Watching some video tutorials, you found out that these are called user interface components and that you're in the process of creating a design system for your application. A design system, you learn, has a palette of colors that all components are meant to share. That way, if you decide to change a color in your user interface, you can do so in the palette and have the change propagating throughout all your components automatically. That's neat! As you start polishing the details of your design, you shift the focus to the interactivity. You want the user to get intuitive feedback on their actions when navigating around the application. So for example, you want this button to glow a bit when the user places the mouse over it. When the user is pressing the button, you want it to glow even more. This makes the application so much more satisfying to use. The problem is that now, for each button color that the palette has, you need 2 extra colors. One color will be the shade that indicates the user is hovering over the button, while the other one will be the shade that indicates the user is pressing the button right now. To support this, you will need to define a set of auxiliary colors, one new color for the hover state and one new color for the press state. But what if you decided to change the colors in the initial palette? You will need to change these auxiliary variations again. What if you want to play around with many palettes, to give the option of different themes to the users? Picking those auxiliary colors now starts looking like a rather cumbersome, repeated task. And worse, because you are doing this manually, the difference in brightness between the main color and the auxiliary ones may become inconsistent, making the design feel sloppy in the end. It does feel that an automated solution should be available for this use case. Is there? Say that you want to find an automated way to approximate the manual process of picking a darker color. An option that you might consider is to place a semi-transparent black layer on top of the original color. A dark layer is a neat solution because when the developers code the application, they don't need to worry about auxiliary colors. To darken something, they just place the dark layer on top of it. The only thing you need to configure is how transparent this dark layer is. Simple. Unfortunately though, it is not good. Once tested with other colors, the transparency level that worked great for the original blue looks okay for this red tone, but pretty awful on white, yellow and green. It seems the solution will not be as simple as a semi-transparent dark layer. There's a lesson here, however. It seems not all colors react to darkening in the same way. Could it be that darkening is a more complex idea than we initially thought? As you research the problem online, you come across the notion of color spaces. Computer color, it turns out, can be described with many systems of 3 or sometimes 4 numbers. You were familiar with the standard one, the RGB color space. It describes a color in terms of how much red light, green light, and blue light it contains. This is a good default, because that is how the vast majority of screens encode color to show it to the user. Each pixel is composed of 3 microscopic sources of light, one pure red, one pure green, and one pure blue. Thanks to the magic of hacking the biology of human color vision, they are enough to reproduce all visible colors. Going back to color spaces, it turns out that the same colors that can be described in terms of red, green and blue light can also be described in terms of hue, saturation and lightness. This is the HSL color space, sometimes also called HSV. Using this new color space, the HSL color space, you can now redefine all your original colors. And it seems this might be getting you somewhere, since the HSL color space contains a lightness dimension. Could not that mean that by tweaking the lightness you can automate the generation of the darker colors? To do that, you take the color that you wanted to transform and the auxiliary color that you picked for the press glow, turn both from RGB into HSL, and check their lightness values to see what the difference is between them. Good. Now you can go ahead and apply the same lightness change to the other colors. Yeah, it turns out that lightness in the HSL color space means pretty much the same thing as adding a black layer on top of the color. Reasonable, but to the human eye it looks completely wrong. But why? Why could a color space that has hue, saturation and lightness as its parameters have a definition of lightness where the same change applied to different hues leads to what feels like very different results? To figure that out, let's look at what a change in lightness in the HSL color space does to the same color in RGB. If we bring down the lightness of a pure red shade by 10 points, from 50 to 40, we can see that the equivalent RGB, which started at 255 red, 0 green and 0 blue, goes down to 204 red, still 0 green and 0 blue. So far so good. As we slide towards green in the hue dial, we can see that the green value increases, but red stays fixed at 204. Red stays at 204 all the way to the color that's supposed to be a darker yellow, but really looks like green mustard to me, which is when green reaches 204 as well. This makes sense. In RGB, yellow is achieved by putting the same amount of green and red light. After that, if we keep moving the dial towards green, red starts to descend, while green stays at 204. This continues until we reach a pure darkish green with 0 red in it. This is all to be expected. It makes sense that if pure red is 255 and the 20% darker red is 204, then a pure green could be 255 and a 20% darker green could be 204. Okay, but why doesn't it look right then? As it turns out, the human eye does not perceive the brightness of all color hues in the same way. So the same amount of red light and green light might be emitted, but the eye will perceive those two differently. The key aspect to understand color vision is that our color and brightness perception was honed by evolution to fit a purpose. Eyes and vision processing in the brain do not function like a camera, which simply captures electromagnetic radiation as it is. Instead, certain parts of the spectrum and certain levels of luminosity have been given a different treatment, selected to be perceived more acutely, highlighting the aspects that are meaningful to our survival. You might have noticed that while plants tend to blur together as a green background, fruit tends to turn bright yellow or red once it is ripe and good to eat. There's nothing coincidental about that. It is convenient for plants to give a clear signal when their fruit is ripe, that is, when their seed is ready to be spread. And it is also convenient to fruit-eating animals like us to be able to tell when fruit is ripe, so we can eat it. The difference in coloration of fruit and the ability of our eyes to pick up that difference co-evolved. It is convenient for the plant and convenient for the human. Now the corollary of this is that there is no reason to expect that vision could treat all colors in the visible spectrum in the same way. And it doesn't. Here is a plot of our understanding of what the perception of color brightness is for the typical human. As you can see, green is the brightest color for us, and, not coincidentally, more or less at the same wavelength at which the sun emits the most intense radiation, with yellow being a close second, red a distant third, and blue being so far down that even the brightest pure blue might be considered a dark color. With this knowledge, let's now look again at the comparison between different hues at 40% lightness according to HSL. Let us add blue to the mixture to have a more complete comparison. Isn't it remarkable how the impact of the brightness change on yellow and green seems to be disproportionately high, while the impact on blue is fairly small? Well, that makes sense. According to our eyes, blue was much darker to start with. The same proportional change in brightness applied to a very light color will be more impactful than when applied to a dark color. A 20% brightness change to 100 is 20 less, while a 20% change to 10 is just 2 less. If we want to have a consistent brightness change for every hue, we need our lightness dimension to control for the human perception. It will not simply be a change where a change in the lightness dials will cause a linear change in the RGB dials. The relationship must now be more complex. We want that a change of lightness that brings down a pure blue by 20% brings down a pure yellow by a lot less, maybe by 5%, to account for the fact that they are perceived of different brightness. That looks much better to me. You can see that to compensate green, we need more change in lightness than to compensate yellow, which doesn't match with the curve below. That is a quirk of RGB, because yellow is full green and full red, which means that twice the light is being emitted for yellow than for green. This is why the changes in lightness dimension do not perfectly match the shape of the luminosity curve. Let's track back. If we were to consider this problem from the start, what is it specifically that you wanted to do? There was this color palette, and for each of the colors in that palette, you wanted to have a darker variation. The assumption was that darkening a color was a straightforward procedure, so there were surely a simple way to automate that. But wow, did that turn out to be a wrong assumption. So, without any longer assuming that, can we rephrase what is it that you want to do? You have a palette of colors and some tweak that you want to do to them. That tweak is in some way coherent, so it seems like a safe hypothesis that a function that does this same tweak for all colors could be extrapolated from the examples. So, you wish to have that extrapolated. You could like to have a function, a mathematical function, that is capable of taking the original color and returns another color, transformed in a way that is coherent with the implicit rules used by your intuition in the original transformation. You could like to have a function that is generated by molding its shape to your source data, to your examples of original palette colors, and transformed auxiliary colors. There are functions like this, and surely they can be generated from good enough source data. In this case, the function is going to take a three-dimensional real vector as an input and return another three-dimensional real vector. We are going to want the function to be total, so that we don't have to worry about potentially feeding it an input value for which it is not defined. And we also want it to be continuous, since we expect it to work in a similar manner for all the colors in the space, without any sudden jumps. Mathematics offers us a large set of tools for defining functions of these characteristics, but why look for anything more complicated than polynomials? Polynomials are great, they are well understood by a lot of people, and they are regularly used to approximate datasets found in empirical science and in engineering. They are fast to compute and easy to describe. Let's start with the definition to ensure that we are all on the same page. A polynomial is the sum of many products, and each product is the multiplication of variables and coefficients. Coefficients are fixed, they are part of the definition of the polynomial, and variables are allowed to change. Because the value of the variables is not fixed, we can think of the polynomial as a function. It is a function that accepts the variables as input, and when computed with the fixed coefficients it holds, the polynomial will give us back a value. Polynomials can also be defined with several variables, but we'll stick to one to make the reasoning easier to follow. Let's plot a simple polynomial on the Cartesian plane. The great thing about the terms of a polynomial is that they add layers of complexity to the curve that the polynomial will describe when plotted on the 2D plane. Starting with the line, the simplest polynomial, we can picture that as we add one term, we get an axle to rotate over. When we add a second term, we introduce another axle, one that the curve bends around. When we add a third term, we seem to introduce another kink, and so on. We can define its shape in this simple way to an arbitrary level of complexity. Since the variables are the input provided to the polynomial, if we order the terms of the polynomial in a certain way, we can represent the polynomial without mentioning sums or products or variables, and focusing instead on the ordered list of coefficients. This list of coefficients fully determines the polynomial. This means that we can think of the polynomial as a vector, which can be defined as an ordered list of numbers. Let us come back to the mapping of colors to other colors. Our problem is framed on 3D color space, but 3D is not a good place to start, because it is too complex to think about. Let's reduce the problem into a simpler form to try to grasp the essentials. Let's imagine that the color that you want to darken is just a pure, fully saturated red tone. Because this particular color is so dominated by red, we can think of the changes in the two other dimensions as being irrelevant, and focus entirely on the red. What we have now is a transformation from the red dimension into the red dimension. This is better. A single dimension we can plot and calculate more easily than 3. Now we can put the amount of red as the value of the vertical axis, and show bars representing an example of what the source red is going to be and what the target red is going to be. Let's add another example. Starting from a darker red tone, we want to darken it even further. We now have a very basic idea of what the transformation should do. How do we adjust the polynomial to it? Let's change the way we plot these colors. Imagine the horizontal axis to be the amount of red in the source color, and the vertical axis to be the amount of red in the target color. We can now place our two example colors as points in this plane. We are looking for a curve. We have measured a couple of points that will help us find it, but we don't know what the best fit will be. Intuitively, each point of data that we add will require us to move it around, and we might want to use the ability to add kinks to the curve to fit the data better. But if there is some noise in the data, some outliers, we don't want to make our curve too squiggly. We don't want to overfit. We want to find some sort of average of how many colors we fit to it. We want to smooth it out. And there is a solution just for that. Enter the least squares method. It goes like this. We have a variable y. We know that it is dependent on another variable x in some way, but we don't know how exactly. We are scientists. We run an experiment in the field and take 6 measures, 6 data points. That is to say, at x equals 2, we measure y equals 5. At x equals 5, we measure y equals 5 again. But at x equals 7, we got y equals 8, and so on. We go back to our desk and plot these points. Is there a model lurking in these points? A line perhaps? Let's start by tracing a line which best fits that data. Why a line? To warm the modeling machine in our minds, we are considering a line, because it is the simplest polynomial. What line to plot? How to choose that line? A very common way to express a line in a plane is isolating y as a polynomial function of x. From this equation, we can see that m is the slope of the line and b is the y-intercept, the value of y when x equals 0. It will be handy for us to write this equation using vector notation. Let's switch terms for clarity. Okay, fine. This form will be useful for us because we know the values of x and y in 6 data points. For example, take the first point, 2, 5, and replace the variables accordingly. Then we get this. Next, we can incorporate the second point, 5, 5, and we get this. Doing the product, we can now work out m and b from this equation. M is equals to 0 and b is equals to 5. This works because the matrix is a square and it is invertible. By the way, if you are unfamiliar with this kind of matrix multiplication, don't worry. I'm leaving a link to a refresher in the card above, but you do not need to understand it to follow the logic of the argument. Knowing how to compute the matrix multiplication is only required if you want to do the computation yourself. Let's plot this intermediate result with just 2 points and see what we get. It's not the worst, we are at least accounting for 2 of the points, but it completely ignores the other 4. Let's see what happens when we incorporate the third point. Actually, this invalidates the previous result. M can no longer be 0 and B can no longer be 5. To understand why this is, let's look back at the graph. This line we had calculated does not pass through the third data point. But changing the line will not do. The problem is not that we have the wrong line, but rather that no line can cover the 3 points. The equation is now what we call overdetermined and does not have a solution. But this is math. When did something not having a solution stop us from trying to solve it? Let's completely ignore that fact and add the 4th, 5th, and 6th and last points. Now, we have turned our initial set of measurements into a single equation, and this is the equation derived from our measurements. Time to name things. Let us call the left-hand side matrix A. The column vector with the incognita, the coefficients m and b, let's call that vector v. Finally, let us call the column vector with the rest of our data b. And so, the equation in the left becomes AV equals b. In other words, if you want to know the values m and b in the equation y equals mx plus b, then you need to find the v such that a times v equals b. The problem being that, as we already saw, that equation in general has no solution. Quick question: what does a mathematician do when facing a problem that has no solution? Answer: invent a way to define one. If we know that no line is going to pass exactly through all of these points, let us invent a criteria that will allow us to say that this line here fits better than this other line here. And to do that, let's start with the case that already works, the case of the line passing exactly through 2 points. If we're going to score lines for how well they fit, this line passing through these 2 points must get a perfect score, certainly higher than this other line that passes through only one of them. One way that we can do this is by comparing the value of y for each x in our source data against the corresponding y in the line that we want to score. We can now subtract the y value for each x and take the absolute value of the result so we get rid of any signs. We can now add all the differences and so we get our score. This score is a measurement of how far away from the ideal the line is. We can see that for a line that matches the data perfectly, the score is going to be 0. And this will give you an intuition of what the least squares method minimizes. To be clear, the cost value that the least square methods minimizes is not simply the difference between the y values, but rather the norm of the residual vector. The details of this are interesting, but it's harder to get an intuition from them, so we started with this analogy. Another way of saying this is that for the perfect line, the norm of the residual vector r equals a times v minus b is 0. But for all others, we are going to have a residue. This residue is that we will call our cost, and that is what we want to minimize. In the least squares approximate solution of A times V equals B, we select V that the norm of the residual R equals AV minus B is minimal. I am going to show you the computation of the least squares method for the 6 data points that we have been talking about. But the goal of this video is to provide a clear motivation for the least squares method and to give an intuition for how it works. The goal is not to go through the computation in gruesome detail. If you would like that, however, we can highly recommend the resources listed in this page from Stanford University, which includes lecture videos available in YouTube and exercises. This has been the resource that helped us make this video possible. And without further ado, the computation. We start with the equation AV equals B. From that, we take the original matrix A and we transpose it so that we get A transposed. We then multiply A transposed by A. We then invert the product and then multiply that inverse by A transposed again. Let's call this product A transposed times A, all inverted times A transposed, the pseudo-inverse. And finally, we multiply the pseudo-inverse by B. And that's it, we get M to be 0.171831 and B to be 5.20094. And that is the line which best fit our data points. So to recap, you have a bunch of data points and you suspect that the polynomial function is going to be a good model for it. You build a matrix A and a vector B from the polynomial and the points. The polynomial coefficients are a vector V so that A times V equals B, and then you calculate V by multiplying A transpose times A, inverting that, multiplying it by A transpose again, and then all of that by B. But what about colors? Don't worry, we're getting there. In the example, we picked a line for regression. But what if we thought that the quadratic function, a parabola curve, could be best? In that case, for the quadratic curve y equals a2x squared plus a1x plus a0, the matrix A and the vector B for the AV equals B equation could look like this. Notice that the first column in the matrix is simply the same value as the second column, but squared. The second column, as a reminder, is the value of our variable x for each of the input data points. In this case, if we follow the computation the same way as before, it turns out that the vector v is equal to this, and the curve is equal to this, which, when plotted, it looks like this. We are very close. Until now, we were working with polynomials with one independent variable, x, and one dependent variable, y. What about a polynomial with two independent variables? No problem, the least squares method stays the same. It is all about finding coefficients. So, for example, take y to be a function from a two-dimensional real space to a one-dimensional real space. Or, put another way, a function that takes x and z as variables. That function, in quadratic form, looks like this. In this case, we could be looking for 6 coefficients instead of 2. That means that to fully determine this polynomial, we need 6 data points. If we have more than 6 data points, then we are back to the least squares approximation, and we can use those points to form the matrix A, to form the vector B, and to resolve the vector V using the least square approximation. And of course, you can extend the use of least squares to problems where the input has more than 2 dimensions, which is good, because that's what colors have, they have 3 dimensions. Now that we have all that we need, if we want to calculate a color, we compute 3 polynomials using the least squares method, one for approximating the amount of red, one for approximating the amount of green, and one for the amount of blue. So, you create many examples of the color transformation and feed them together to the least squares algorithm. Out comes a function. Let's throw some random colors at it. Let's try this one. That looks good. What about this one? Not bad. This other one? Good too. And this is our solution. You can now go back and re-implement the color palette as many times as you need. The auxiliary colors will be there automatically, always defined for you. With this algorithm, you automated the part of you. You have molded the function into the shape of your perception. And what's even better, you now have the tool to do that for any color transformation that you can think of. And who knows, maybe even more than just colors. Isn't that neat?